Hello everyone, welcome to this video. In the last video we saw reducibility of a polynomial which is of degree 2 and of degree 3. In this video we shall see some more irreducibility test for polynomials which are of in some general sense, right? So the first result is that reducibility over rationals implies the reducibility over integers. That means if you have some polynomial which is reducible over the field Q, that is the field of rationals, then it is also reducible over the field Z of integers, right? So the theorem is if you have any field if you have any polynomial f of x from the from this ring of integers, right, and if fx is reducible over the field of rationals, then it is also reducible over z. So let us look at some example. Suppose this is the polynomial given to us, then this polynomial is reducible over q. Why? Because we can factorize this as these two polynomials where the coefficients of these two polynomials, they belongs to the set of rational numbers, right? So now this polynomial, because it is reducible over q, it is also reducible over z. So why this? And this is also true because we can also write this polynomial like this. So it implies that if you know that the given polynomial, it is reducible over q, then you can directly say that this polynomial is also reducible over the set z of integers, right? So this is the one result. Next is second result, which is mod p irreducibility test. So this test is quite useful. And what does it say? It says that if p is any prime number and we take any polynomial from zx whose degree is greater than equal to 1. Now here look, we can take polynomial with degree greater than 3 also, unlike the previous case. So what you need to do in this, so let fx bar be a polynomial in zpx obtained from fx by reducing all coefficients of fx modulo p. That means whatever is this polynomial, each coefficient of this polynomial is reduced to modulo p, right? And now this reduced polynomial f dash x, this is checked over this zpx, right? If this is reducible over zpx, then the original polynomial is reducible over q, provided the degree of the original polynomial and the one which we have reduced is same, right? So this is the result. So here one should note that if we find one such prime numbers for which the reduced polynomial is irreducible, so that would be sufficient to prove that the original polynomial is also irreducible, right? So let us understand this result by seeing an example. So this is the given polynomial. This is of degree 3, right? So we can apply the previous result also. That means if we are able to find any root for this polynomial, we can directly say that this is irreducible, right? So now the degree of this polynomial is 3, which is greater than 1. So according to the above result, what we need to do is we just have to make another polynomial f bar x, right? So how can we create that? Now the first task is you just write the terms as it is: x cube, x square, and x, and then constant, and you just have to apply mod p over this. So for that we have selected mod 2. The first prime that comes to our mind, that is 2, right? So 21 mod 2 would be, when you divide 21 by 2, the remainder would be 1. So here it is 1. Next, minus 3 mod 1. So it would be minus 1, right? Minus 3 mod 2. Again, 2 mod 2, that would be 0. And 9 mod 2, that would be 1. So this is the reduced polynomial. Again, the degree of this reduced polynomial is same as the degree of the original polynomial. So we can apply the above test. So for that we need to check this polynomial, whether this is irreducible over Z2. And Z2 contains two elements, 0 and 1. We all know that. So to check whether this is irreducible over this or not, this is of degree 3. So we need to check whether there is a root of this polynomial or not. So for that, we just check whether this is a root or this is a root. To check that, what we do, we first calculate f of 0. So what would be that? It is 1 after calculating and solving. So this is not equal to 0. So this is not a root. Again, f of 1, what would be that? It is again 1. So this is also not a root. So we have no root in this set. So by the previous result, which was discussed in the last video, so this polynomial f bar x, this is irreducible. So accordingly, using this test, the original polynomial fx is also irreducible over the field of rationals, right? So this is as simple as that. That means you just change the given polynomial to some mod p, where p is any prime. You can check it for different primes, and if you get at least one prime, then whatever is the polynomial, you check that polynomial whether it is irreducible over the given finite field. It could be easily done, right? So if this reduced polynomial is irreducible, then the original polynomial is again irreducible. So this is the test. The main property for this is, this test is also useful for polynomials having degree greater than 3. Moreover, this could also be applied to polynomials having rational coefficients. So let us look at another example with rational coefficients and degree greater than 3. So let us take this polynomial fx is equal to 3 by 7x to the power 4 minus 2 by 7x square plus 9 by 35x plus 3 by 5. We need to check whether this polynomial is irreducible over the set of rationals or not. So for that, what we did is we created another polynomial having integer coefficients. So how can we do that? We take the LCM of these denominators, that would be 35, and then we multiply whole of this polynomial with 35 and we obtain this. So now this polynomial has all the coefficients as integers, right? So now to check whether hx is irreducible over z or not, we have to create an h bar x, right? We need to create the reduced polynomial h bar x. So we'll start with mod p irreducibility test by testing for the prime 2, right? So if the polynomial hx is irreducible over z, so according to test 1 in this video, this fx will also be reducible over the set of rational numbers, right? Over the field of rational numbers. So for that, we first convert hx to h bar x and we test it for mod 2. So what was our hx? Our hx was 15x power 4. So it would be 15 mod 2. What would be 15 mod 2? When you divide 15 by 2, you'll get the remainder as 1. So it would be 1x raised to power 4 minus, when you divide 10 by 2, you'll get the remainder as 0. So it is 0. 9 mod 2 is 1 and 21 mod 2 is 1. So this is our reduced polynomial. So now we need to check whether this polynomial is irreducible over Z2 or not. So we need to check this. To check whether it has any linear factors, because now we cannot directly apply that test for which was defined for degree 2 and 3, because here the degree is 4. So we have to see if there are any linear factors or we can somehow factorize this polynomial. So let's check that. Let's start with the linear factors. For linear factors, we'll just check whether this polynomial has a root in Z2 or not. If yes, then it would have linear factors, and in that case it would be reducible, not irreducible. So let's check that. So for checking that, our set is Z2. And what is that? 0 and 1. So you just have to check h bar 0, that is 1. So 0 is not a root. h1, that is 1. So 1 is also not a root. So that means there are no linear factors. So h bar x has no roots. So from here we cannot directly say that it is irreducible. We have to check whether there are some other factors possible or not. So we'll check for quadratic factors. So the general form for this quadratic factors would be x square plus ax plus b, right? Where a and b could be any elements from Z2. And what kind of elements Z2 has? It has 0 and 1. So we have 4 possibilities. First is you can have a as 0 or 1. So this is 0 and this is 1. And for b, you could have 0 or 1. So 0 or 1, 0 and 1. 4 possible factors could be there. So now we'll check for each of these factors. Now this factor has a 0 bar. That means you can factorize this as x square plus 1, right? X plus 1, right? So therefore h bar x does not have a 0. This factor has a 0, but we have proved that h bar x does not have a 0. Let's see that. H bar x has no root. So this cannot be possible, right? So this factor could not be the quadratic factor of h bar x. Next we'll check for h square 0x plus 1. So this also has a 0. That means when you substitute 1 in this polynomial, what you'll get? You'll get 0. Because 1 square plus 1, that would be 2, and 2 mod 2 would be 0. So 1 is the root or 0 of this polynomial. However, because we are seeing this factor as this polynomial as a factor of h bar x, and h bar x has no roots, therefore this must also have no root, but we found one root, therefore this cannot be the factor, right? In a similar way, the third one is also ruled out, and the fourth one, it has no zeros, therefore it could be a factor. Let's check whether this is a factor or not. So this could be checked by the process of long division. We can divide our h bar x, this was our h bar x, with this factor. So we'll get this, but the remainder in this case is not equal to 0. That means this factor does not divide this h bar x. So therefore this is also not a factor. That means there are no quadratic factors of h bar x. Hence h bar x is irreducible over Z2, and if this is irreducible over Z2, that means hx is irreducible over Z, and that means fx is irreducible over Q using the first test, and this is using the second test. So we say that the given polynomial is irreducible, right? So so you see, for degree 2 and degree 3, it is so simple. That means you just find a root and you just say that if the polynomial has a root, so then it would not be irreducible, and if it doesn't have a root, it would be irreducible, right? But in this case, you have to do some other things also, right? So to conclude, in this case, what do we say? We say to conclude whether a particular polynomial in Zx is irreducible over Q, what we have to do? we need to find one single prime number for which the corresponding polynomial, the reduced polynomial in ZP is irreducible. If you find such P such that the reduced polynomial is irreducible, then the given polynomial is also irreducible over the field of rational number. But if you fail to find any P, that means you cannot find any P, in that case, we cannot conclude that the given polynomial is irreducible over Q. That means you cannot go the reverse. You cannot say it conversely. This is one directional result. So I have an example for this. Suppose this is our polynomial and this is reducible over ZP for every P. That means you cannot find any P for which this is irreducible over ZP. So the converse result should state that the given polynomial is reducible, but this is not the case. This polynomial is irreducible over the field of rationals. So hence the converse of mod P irreducibility test is not true. So keep that in mind always while using this test, that this is one way result only. So we have discussed two tests in this video. In the next video we shall again see one more test known as Eisenstein's criteria for checking the irreducibility of polynomials. So that is it for this video. Thank you for watching.